Hi, welcome to Unit 3, Day 1, Part 2, Wave Nature of Light. So we already saw in Part 1 that light has both a particle and wave nature, or behaves as a particle and a wave. So in this section, we're going to focus on the wave properties of light. Now, since light has a wave nature, that means that it will also have properties that you find in any wave, like wavelength and frequency. Let's start off by talking about the wavelength. So wavelength measures the distance between two peaks or troughs of a wave. So for example, we can measure the distance between these two peaks, and that would represent one wavelength. Or we can measure the distance between the two troughs at the bottom, and that would also represent one wavelength. And these two values will be the same. Now, the units that we use to measure wavelength will be the units we use for any length, right? We would normally use meters, or we could use inches. But typically for waves, when dealing with electromagnetic radiation, the units are in nanometers. And 1 nanometer is equal to 1 times 10 to the negative 9 meters, which is 1 billionth of a meter. Conversely, 1 meter would contain 1 billion nanometers. All right, let's talk about frequency next. So frequency measures the number of waves that pass a given point in a certain amount of time. And if you measure that time in seconds, then the frequency will be in hertz. And 1 hertz is equivalent to 1 over a second. So let's take a closer look at that. Let's say we have this point here, and we're going to measure how many waves will pass this point in 1 second. Okay, so for our first wave, the red wave on top, a total of 2 waves passed in 1 second. So that means that that wave has a frequency of 2 hertz. Whereas for the bottom wave, the blue wave, a total of 1, 2, 3, 4, 5 waves passed in 1 second. So that would have a frequency of 5 hertz. Now, one thing you may notice is that the red wave, which has a longer wavelength, has a shorter frequency. And that makes sense because since the wavelength is longer, it will take more time for a full wave to pass through. On the other hand, the blue wave, which has a shorter wavelength, has a higher frequency because it will take less time for one wave to pass through. Okay, now that we looked at wavelength and frequency, the next thing we're going to look at is speed. So light travels, but how fast does it travel? Now we know that speed can be measured as distance over time. So for light, the way we do that is we use wavelength, which is our distance, and we multiply it by frequency, which is measured in hertz, or gives us the number of waves that pass in a certain amount of time. So if you multiply these two values together, your distance and per time, you get your speed. Now, speed of light is also a constant, and in a vacuum, that constant is 2.998 times 10 to the 8 meters per second. So that's the fastest that light can travel, because in a vacuum essentially means there are no particles, whether it's air or water or whatever. There are no particles to interfere with light, so that's the fastest it can go. So let's sort of recap, and this is where you'll take your notes in your note packet. So wavelength and frequency are inversely proportional, and that means that as the wavelength increases, the frequency will decrease by the same factor. So for example, if you double wavelength, the frequency will be halved. And this relationship is quantified by the speed of light equation. So let's take a look at this equation. Once again, c, which is the speed of light, is equal to the wavelength times the frequency. And in your notes here, you're going to note the value of speed of light, 2.998 times 10 to the 8 meters per second. If you're using that as your constant, then your wavelength must be in meters and your frequency must be in hertz, or 1 over seconds. All right, make sure you capture all these notes down. And if you need to pause the video, do so before we move on. Okay, so looking at the proportionality of, or the relationship between frequency and wavelength. So as frequency increases, the wavelength must decrease since the speed of light is a constant. So in order to keep that speed of light constant, as frequency goes up, wavelength must go down. And this sort of proves or shows that both are inversely proportional. All right, there are a few CFUs. So the first CFU, CFU2, has 3 parts, A, B, and C. A and B you should be able to answer with the information that you gained in this section. C you may be able to answer from previous knowledge. But if you can't answer C, just know that I will provide the answer after in the last part of this video lesson. So pause the video now, try the CFU, and when you press play again, the answers will be revealed. All right, here are the answers for CFU A and B. Take a moment to read them. CFU 2C, I will give you the answer after part 3. Okay, finally, CFU 3. Try this CFU and pause the video, and when you press play again, the answer will be revealed. So in this problem, they're asking you to calculate the frequency, and they give you the wavelength in nanometers. So the first thing you need to do is convert it to meters, because we're going to plug it into the speed of light equation here. And so wavelength must be in meters. So once we do that, we can go ahead and plug in our speed of light, which is a constant, and our wavelength. And then we just use inverse operations to solve for our unknown, and you get a frequency of 5.09 times 10 to the 14 hertz. All right, that's it for this video. Move on now to part 3.